Hello, good morning. Welcome to Rigaku webinar. My name is Magdalena Grzywa and I will be co-host during this webinar. I see we have almost 100 people already on this call, so let's not wait too long for others to join. We will anyway start with the short introduction, so will be enough a moment to join for the next. The webinar today is the determining the rare earth elements in geological minerals accurately using X-ray fluorescence. You will be muted during the webinar, but of course you are very much welcome to ask the question. Please ask your question in the Q&A session, because in this format, the Q&A session, question will be saved. And since we have more than 100 people already, I can imagine that we will have a lot of questions after the webinar. And we will answer all of them per email if the time doesn't allow to answer them live. If you have any trouble technically, you can always contact us over the chat. Then we will try to help you and support you. And our presenter, Carmen Kaiser-Bruckmann, works many years in industry, has solid analytical knowledge and experience. And since many years, she is already application specialist at Rigaku Europe, supporting a lot of customers from different markets with the XRF knowledge calibration and experience and support. Yeah, welcome one more time from my side, and Carmen, the stage is yours.
Thank you very much, Magda, and I will talk to you later with hopefully some interesting questions. Yes, if there are any difficulties, Magda will support you, as mentioned. So I would like to, before I start with my introduction to the topic, I would like to just point out that this is our main portfolio for wavelength dispersive instruments. We have the floor standing instruments. These are all sequential, these three. So the Primus series, as they are known, and then the simultaneous instrument, which is the Simultex, and our very nice benchtop WDXRF, which is the Super Mini 200. So as you can see, they have different requirements and different places. Today, I will focus on the Primus 4. So all the measurement and work that I will show was based on Primus 4. I will also talk briefly about some measurements that were done with one of our customers with the Primus 4i. So you will get some nice information about what is possible with wavelength dispersive instruments from Rigaku. So the topic that we are going to talk about today is the rare earth elements, and I will do an introduction followed by some examples where rare earth elements are used. I will talk about our unique hardware and software features. I will mainly talk about the pressed powder method. We will also bring in some other examples, analytical examples, and I will talk briefly also about scattering ratio, which is a correction method for trace element analysis. I will also talk about how we can set up calibrations, and most importantly, the analytical parameters that are used for setting up these methods for rare earth elements. Okay, so as an introduction, XRF is used for the analysis of rare earth elements for majors, minors, and trace elements in the materials with a natural origin, and also for some industrial products containing rare earths. basically for major, minor, and trace elements. Commonly, we use the ICP-OES or ICP-MS methods, but it's generally quite complicated with extraction and acid digestions and daily calibrations. So we like to use XRF. Very often XRF is a more rapid technique where you can have a lot of sample throughput. And very advantageous is that we have a direct analysis of the solid material. So we can analyze these rare earth elements either with wavelength dispersive or energy dispersive XRF. The problem with XRF is it does not have the same level of limits of detection as an ICP-MS, but in most cases it's more than enough, and we can also reduce the error that we have with a limit of detection with actually a fusion or even a pre-concentration method. So it is possible. So I will show you some of these examples. Very briefly, maybe some of you are not familiar, but of course WDXRF has the advantage in that we get best separation and resolution with the elements by using the crystals that we have here. An energy dispersive is a very simple kind of method, and it's really basically used for screening purposes. So it's a very simple kind of measurement. And here we measure the number of photons in the form of an energy. So here you can see we have at Rigaku WD an energy dispersive, a very simple design here in comparison to a WDXRF. So this instrument offers the highest resolution and sensitivity. You will see some examples later. And it's commonly used for rare earth oxides. It is obviously a larger instrument. This is a sequential measurement, whereas this is more a cheaper kind of instrument. You can also get a handheld instrument, a lower tube, a current and power. But of course, this is much better because we get better limits of detection as compared to something like this. So you can see some examples here where WDXRF is used, and today we'll focus on rare earth materials, and which is where we will use the primers for. So, of course, why are rare earths so important? So if you look at the news today, we see a lot of research and development into why rare earths are so important. Actually, in Norway, they've discovered a new deposit of rare earths. So it's one of the largest rare earth metal deposits found. And basically, these elements, as you can see, I've made some pictures here of some of the rare earths. So like, for example, praseodymium is used to create strong metals in aircraft engines, for example. It is also a component that can be used in a sort of glass for protection of welders and glass makers. For example, the lanthanims, this element is used in, for example, cameras and telescope lenses. And lanthanides are also used extensively in carbon lighting applications such as studio lighting and cinema projection. You get neodymium. This element is very powerful in making magnets used in loudspeakers and computer hard drives to enable them to have a smaller and more efficient working. So the magnets containing this element neodymium are used in green technologies such as making wind turbines and hybrid cars. So very important elements. Cerium, for example, is used in catalytic converters in cars, enabling them to run high temperatures and playing a crucial role in the chemical reactions in converters. So, for example, the lanthanum and ceriums are also used in the process of refining crude oils. So you can see a very large field of applications where we use rare earth elements. So in general, catalysts, magnets, metals and alloys, ceramics used in capacitors, scintillators, colorants, phosphors, glass and polishing for UV-resistant glass, X-ray imaging. So, and of course, we can also use it in nuclear defense, water treatments, and fertilizers. So the principal economic sources of rare earth minerals that are mined are namely basanites, monzonites, and the estimated average concentration of the rare earth elements in the ranges from about 130 to 240 micrograms per gram, which is not a lot. And of course, the unique catalytic, metallurgical, and electrical and magnetic properties are very useful in producing a lot of basically used for the group that you see here. So, for example, in the last 3 decades, there's been a lot of applications for rare earth elements and their alloys to support the technology that you see here. So you can look at the slides later, but here you can see a list from scandium all the way through to latunium, which element is used for which kind of application. So, of course, let's look at how we can basically take these minerals from the earth and basically try to estimate and to try to accurately actually measure these rare earth elements using wavelength dispersive XRF. So if we take our Primus 4, the biggest advantage of this kind of instrument is that we have the geometry being above the sample. So this enables us to have a very high sensitivity and precision with the lowest limits of detection, which is what we would like to achieve. We also have a very nice system in that we can use automatic pressure control, which helps us to analyze these mineralogical elements that we would like to measure. So I will show you some examples of fundamental and empirical calibration methods to measure these kind of rare earth elements. And I will also give you some examples of these very special crystals that we have in our instrument, which are the Rigaku crystals, to give better separation and resolution of these rare earth elements, because they're very complicated. They have a lot of line overlaps. So in particular, we have the LIF420 and the LIF220, which will give you the best sensitivity. So let's look at this examples of some of these groups that you see here of rare earth elements. So, of course, we have to start with the sample preparation. And, of course, in most cases, we will use the pressed powder method for preparation. So very important is to have the correct particle size. And, of course, we need to have homogeneity within the pressed powder. So pressed powder method suffers from matrix and mineralogy errors. So we need to try to make the use of the fundamental parameters method. We also can use in our software something which we call the scattering ratio correction method. So it helps us to improve basically the method for best accuracy and precision for these trace elements. So if we look at the pressed powder method, we need to have a defined density. Particle size needs to be less than 45 micron. And in this example, we need to get maximum penetration depth depending on the energy of the fluorescent radiation that we need to measure. So we need to have at least an infinite thickness of 4 millimeters to be able to get the correct penetration depth. So, of course, if we look at our software, we have a very nice feature in that we can use together with our quantitative method something that's called the ratio correction method. So this means that we can measure basically the Compton line for that particular element and ratio it together with the analytical line. So this helps us to improve the accuracy of that particular element. So here we can see an example of a trace element where we just plotted an empirical calibration, where we plotted the concentration in ppm versus the intensity of the analyte line, and you can see there's a lot of scatter. But the moment that we can measure for each and every standard the Compton line, and we can ratio the analyte line with the Compton line, we suddenly get a very improved regression and accuracy on this calibration line. So this is a very useful method that we can utilize. So here you can see this example where we looked at a niobium, and you can see the standards, and we used this ratio correction method, and we also split the calibration into two different parts. So this is also a very nice and useful part of our software. So the golden rule for accuracy with XRF is that the highest accuracy can be achieved by comparing the unknowns with the standards with as much as a similar mineralogy, particle size, and particle homogeneity as the matrix characteristics. So the standards that we use need to match the range of the sample concentration as well as the matrix composition. So our aim is to cover at least 95% of the natural distribution range. So this is a very important part that we often forget. So the standards used for a calibration of rare earth are very difficult to find, and so therefore we can try to use secondary standards where we can certify this in a central laboratory, a commercial laboratory, if you like. We can also use other techniques to improve and get proper standards for these range of elements that you see here. We also have a starting point in Rigaku, which is called our Geological trace pack. Of course, it doesn't include all the elements that you see here, but we can start with this package, which consists of 101 certified reference materials, and we can rename this method and extend the calibration range by also adding additional elements if we wish. So before we can start with the calibration, it's important for us to basically undergo massive sample reduction, because of course these minerals are basically mined and they consist of large rocks. So we need to ensure that the particle size reduction is done in a decent way. So this means we need to follow the steps that you see here to give a proper homogeneity to this material and to reduce particle size effectively to get an overall sample that we can measure with a considerable amount of accuracy. So in order to verify our calibration methods, we can also get some reference materials. Here are some examples of some reference materials that contain these rare earth elements. So some of them are the NIST standards, some of them are from the Geological Survey of Japan. We can also get the SAM Mintek South African standards. We also have the British Geological Survey standards. And we also can get the USGS Geological Survey standards. So these are quite expensive, and we should try to use them effectively in our laboratory to do the verification of our method. So here you can see some examples of K-line spectra of the rare earths using the LRF220 with a 0.15 collimator and a scintillation detector. So the rare earths have 3 K lines and about 7 different L lines, which can be used to develop our methods. However, the sensitivity of these lines differs a lot from the K series, the K alpha line, and the L lines of the L alpha ones can show the highest sensitivity. So typically, the elements lanthanide, cerium, prosidium, neodymium, and samarium. In the pressed powder, we can use the K series of lines, but this is based on a large penetration depth, and the particle size effects will be reduced. So the spectra of these K lines for these elements can be measured with the crystal that I mentioned. And here's an example of the spectra. So you can see there's a lot of overlap. And of course, it's important for us to separate this. So here you can see an example of some L lines that can be used with fusion disks because of the infinite thickness limitations. So here you can see the lanthanide, gadolinium, and the lutetium, where we used the rhodium target, but here we used LRF220 as well with the scintillation and flow proportional detector. And you can see that we have separated the lines quite nicely here. Here's another example where we have another part of the spectra, and the most difficult work in creating these application programs or measurement programs is the selection of the analytical line and choosing the correct positions because of the high number of line overlaps. So it's very difficult to give you an overall recommendation, but I took the spectra of a glass standard, which is an FLX S13 standard, to show the full spectrum of the analyte lines and the regions of interest for the rare earth elements. So this kind of standard can help you to give you a detailed study of the line that gives a good impression, where we can select the correct background positions for the application. So here we have a zooming in of these particular elements, and you can see this is also with the LRF220 and the flow proportional detector. So if we zoom in a little bit more, you can see the lanthanides are separated here with an L alpha 1 and L alpha 2 lines, for example. So this can help you to choose the correct peak angle and background positions. So this is an example of the recommended analytical lines. So from atomic number 57 to 71. You can see how many different lines are possible here. We can also look at an example of the line overlaps from 3 to 10 kilo electron volts. So you can see the scale here. And for example, you can see, if you look at lanthanide or promethium, you can see that all of these have these overlaps from all the rare earth elements. So this can be very helpful when doing the method development. So here you can see some more examples of the analyzing crystals. So the same spectra in all is shown, but here you can see if we use LRF200, we can see that if we switch to LRF220, we drop here, but we get a little bit of separation. But of course, the LIF420 gives you the highest resolution, but so we really get a good separation here. But of course, we lose some sensitivity in this particular element. So here you can see some more examples here of ytterbium. So you can see that the LIF220 at the bottom here gives a very good separation here. But of course, we lose intensity. So here you can see the intensity scale. So we do get separation from nickel, but of course, we lose intensity. But of course, for method development, we want to get a proper peak angle and a proper background correction. So therefore, we try to use this kind of crystal. Here's some more examples of germanium. So the LIF220 crystal shows best separation and resolution from germanium K-alpha. And the sensitivity of germanium is now lower due to the loss of intensity. Once again, you can see the intensity scale here. Good separation, so at least we can now define a proper peak angle and a proper background, but it offers you best separation, but low sensitivity. So here you can see an example of the comparison of WD and energy dispersive XRF limits of detection. So you can see that WDXRF, the measurements were done with 20 seconds per line using a lithium tetraborate matrix, and we compare it to 600 second with energy dispersive in a cellulose matrix. So from lanthanide to europium. Here's another example, but now using the L lines, okay? So the first was the K lines, and now you can see the L lines. So you can see with the L lines that we get a much better limit of detection for WDXRF in the same matrix with lithium tetraborate as compared to energy dispersive XRF. So very briefly, I would like to show you the GeoTrace pack, which is established with 101 CRM materials, and it's a really nice solution for your laboratory for trace element analysis and major oxide analysis, and it's based on the pressed powder method. So we have 26 trace elements. This is an example of the trace elements. And then, of course, we also get 26 of them ranging from scandium to uranium. You can see the analytical range and the type of accuracy that can be achieved with this method. So this is the example of the major composition of this package. Silica is set as a balance, and basically the calibrations are divided into low concentration and high concentration ranges. So what's very nice as a starting point for your lab is that you will be given a recipe on how to prepare this pressed powder method, and you also get drift correction and validation samples. You are also able to extend the calibration, as I mentioned earlier, with the additional secondary or reference materials. This is an example of one of the validation samples that is supplied with the package. So, of course, you can measure the sample to check the integrity of the method and to monitor when it is needed to do, for example, a drift correction on the method. So here you can see an example of the reference values and the comparison with the analytical result that can be achieved with or without a binder. This is another type of reference materials where you can have a different range for the verification and validation of this method. I would like to share some alternative methods of analysis in the rare earth elements. So recently I was at the University of Uvascular, one of our customers, and they were very kind enough to share some data. So this is in Finland, and they have the Primus 4i. If you are interested later, we have some very nice reference to the research project that they are involved with, so you can scan the QR code to have a look at some more information. So while I was there, they were analyzing some rare earth magnet powder. Because they only had a very small amount of powder, they used an alternative method using a loose powder cell. So here you can see this loose powder cell. And they used our semi-quantitative analysis program to look at the spectra of this material. They didn't really want to know the accuracy here. They just wanted to see the elements and to see what is present. So you can see some nice spectra here with the different measuring conditions shown above. In our software, we are also able to use the deconvolution of the peaks here, and you can see the information here. Some more examples where we can see the deconvolution and looking deeper into the spectra. So this is an example of what kind of analysis you can get from our semi-quantitative, which is our standardless program. So it gives you a very nice starting point to just identify what's present in the material before you can start to set up calibration methods and so on. So what's very useful about our semi-quantitative analysis is that we can see, for example, some more details in terms of detection limits, the analytical line that was measured. We also get some very useful information about the analyzing depth. So this can be useful for later on for method development. So basically, in geology, we can use drill cores and prospect analysis to draw up a mining plan, because we need to ensure that when we do the mining and the blending of various ores and deposits, we need to extend the life of the mine. So here you can see some examples of tantalum and niobium ores, and some of these need to follow some mineralogical material analysis and groups and elements. So here you can see an overview of different raw material analysis, but in particular we can look at rare earth minerals. So here are the group of them that you can see. So they belong to this non-ferrous metal group. Yeah, of course, with the analysis, we can also use what we call the analysis of rare earth magnets. So we can do mapping of this particular magnet. So here you can see some examples from our software. So it's quite useful because we can load the image, and you can see the image here. We can select a grid or points if we want, and we can link this analysis to either a semi-quantitative or quantitative method, and we can try to map and have a look at the richest part of this magnet. So we can look at, for example, the intensities, and we can say that this kind of data can be used to fingerprint the elements so that we can see the homogeneity of this magnet surface. So it can be very useful for this kind of work. So here we have another example from our WDXRF where we had big magnets and smaller magnets, so we can load them with different sample masks. So here you can see a 10 millimeter and a 20 millimeter mask to basically have a look at this magnet. So here you can see, once again, we only use semi-quantitative analysis, and we looked at the magnets to see what was present in the magnets. So here you can see the gadolinium and the niobium that's present or not present, and what's major and minor analysis here. So it could be very useful for you to understand how this particular rare earth magnet was produced. So another example of some milled and dried powder that was presented to us by one of our customers. We compressed this yellow powder that was concentrated with cerium, for example. Here we also have a lot of zirconium in the powder, so it can be very useful for us to understand what is present in this kind of powder. Another example of some rare earth applications in XRF is that we can even use these liquid samples and set up calibration methods. So we had some concentrated standards that were presented to us with mixtures ranging from lanthanides to gadolinium. And basically, how did we prepare these liquid samples? So we used what we call an ultra carry method. So here's an example of this kind of filter that's available with Rigaku. So we placed a dedicated amount of liquid and we dried it in a vacuum dryer. And we were able to load these into what we call our backscatter cup, using the equipment that you see here. And we could try to set up this calibration method that you can see here from our software. And you can see that we can set up these elements very nicely using this ultra carry method, which is known as our pre-concentration method. Some more examples of calibrations. So you can see some summary of the calibration. So you can see that we can very nicely set up a good correlation with a good accuracy shown in ppm for these elements that you see here in the liquid samples. What's also important in XRF is to try to establish what kind of repeatability we can achieve with the instrument. So using these calibration methods, we can do repeatability, and in particular static repeatability. So meaning we could prepare the sample several times, measure the sample several times, and try to see at the 95% confidence level what we can achieve for the elements that you see here. So you can see that we can achieve very good static repeatability measurements at the 95% confidence level using this method. So basically, in conclusion, I just wanted to share with you the different ways that we can measure the rare earth elements using our spectrometer, how we can use our different analyzing crystals to achieve the best resolution and sensitivity. Of course, we have application packages available with our instrumentation, and in particular, we have the GeoTrace pack, which I briefly mentioned. We also have an oxide fuse bead pack, which can be very useful for the additional quantification of the major analysis of a particular kind of geological material. And these two packages can give you a good overall quantification for majors, minors, and trace elements. So in general, please contact us for some more details on our hardware and software that we can offer you. And as you can see, that we can offer you the best stability and consistent measurements from the small examples that I tried to show you. Our software is very easy to use, and you can see that we have many different software modules available to try to help you to quantify the different materials that you have, being it a solid, a powder, or even a geological mapping that you would like to do on a particular rock. So I just try to give you an overall view of some of these applications. So Magda, I don't know if you have any questions that are maybe if we have some more time, perhaps.
Thank you very much, first of all, for a great presentation. Yes, indeed, we have some questions, but maybe I will pick just few and the rest we will answer. I was already answering some of them to you over the chat. So I think there was 2 times the question about the loose powder method. So because there is a common problem that the material there is not enough material for analysis to prepare the stable pressed pellet.
Okay.
So maybe you can explain the loose powder sample preparation, and there is also the question: is there a minimum sample thickness or mass depending on the K and L lines for the rare elements, earth elements?
So yes, here in particular we have a very nice powder cell. We call it a powder cell. There are many different kinds available with Rigaku, but here's one example. Here you need to have a bit more sample than the other examples, but this gives you a very semi-quantitative analysis, of course, because if you don't have a lot of sample available, then, what do? You cannot prepare a pressed powder. Yes. Well, sometimes you can have a double pellet method where you could have a backing of boric acid and you could sprinkle the sample on top. But then it's very semi-quantitative analysis. But this is a very nice solution from Rigaku. It's recyclable. So it means it consists of a plastic cell with a nylon filter here, and we could place the dried and milled powder into the cell and place it with a film on top with a snap-on ring, and we end up with a powder cell that looks like this. So it looks very nice because we have a nice representation here. Of course, problem is, we might not have a sufficient amount of thickness for the analysis of this. So, of course, our software helps you to understand this. So originally, we had some examples here to see the analyzing depth. So the fundamental parameters module in our software will calculate the thickness that's needed. But in general, if you have enough powder, it is better to have a sample that is infinitely thick. So our aim with pressed powder is always to get 4 millimeters thick pressed powder. But if you don't have enough, then we could try to use this kind of cell. But once again, it's very semi-quantitative. Okay, so not accurate at all. But it is a starting point for you to understand what is present in the material. We also have some other examples of cells, different powder cells, where we have a similar kind of cup, but with sample board inside, where you could achieve only a 1 millimeter thickness because, it has a little powder diameter of 10 or 20 millimeters, where we could place even a smaller quantity of sample inside the cell, also with a film on top. But once again, it's also very semi-quantitative, but you can measure a sample like this. We even tried to use this kind of method that you see here for catalyst samples. So here you can see a powder, it's actually a catalyst. And we try to also create calibration methods. So, of course, if you try to create calibration methods, then of course your method should try to be the same as exactly the same, if possible, if you would like to achieve something with a calibration. So, if it's pressed powder, it should be prepared in exactly the same way as the unknowns. So unknowns and standards need to match as closely as possible. Yes. Sorry, there was another question, maybe, Magda? I think
yes.
we run out of time, or
no, maybe one more. I was seeing here. For heavy elements determination, which sample preparation you prefer, pressed powder or fused beads?
Yeah, so in one of the articles that we have, we can have basically fusion and pressed powder. Of course, fusion will dilute your sample, but the advantage, of course, with fusion is, of course, that we take away the error related to particle size, matrix mineralogy. So it really depends on the level that you would like to achieve and how you would like to achieve it. So the biggest advantage with the fusion method, of course, is that we can even try to prepare synthetic standards. So not only the use of certified standards, but also maybe we could try to spike it and make these synthetic standards. So it's also a big advantage over a pressed powder method. Of course, pressed powder method is always good because we don't have too much dilution, but then once again we have this very nice advantage with our software in that we can create these fundamental parameters calibrations, so which can be very useful for the geological world, because if you have empirical calibration, we need to have as closely as match with the matrix and mineralogy. And this is not always so easy because we cannot always find the same match of standards with matrix and the mineralogy. So both, yeah.
The last question, maybe before we will close. What do you recommend when performing a calibration curve with standards containing major and traces elements? Shall I repeat the question? I think I understand that there is the question if in one calibration should be major and traces, or if we should have dedicated calibration with only traces.
Yeah, so this is always important to separate the two. So you should try to have a calibration for trace elements so that you can spend enough time and the correct preparation and method of approach. So try to separate the traces into one and then the majors and minors in another. So very often we use major and minor with the fused bead method, because this is much easier this way, and trace elements mainly with the pressed powder because we don't have a lot of dilution here with this. And of course, the biggest advantage with our Primus 4 is, of course, we can, depending on the nature of the material, we could get away with a very small amount of binder, or sometimes even go without a binder. So some of the nature of the geological materials can be without a binder. So this means we have a very concentrated material and we can get much better signal when we don't have too much binder in our pressed powder sample. So that's why in our geological trace calibration method that we offer at Rigaku, you can get away without a binder if the nature of the material presses very well. Of course, if you have a lot of silica and zirconium in this kind of mineral, then it's sometimes very difficult to press it without a binder. It can crack very easily. Of course, we don't want to introduce an inferior sample into our spectrometer because there will always be problems with the contamination of our chamber, of course, even though we have a tube above.
Okay, thank you so much.
Thank you, Magda.
Thank you, Carmen, for your great presentation one more time, and thank you to all attendees who joined today Rigaku webinar, and hope to see you soon on the next coming webinars.
And once again, thank you very much to the University of Uvascular for sharing some of your great samples and spectra. Thank you very much.
Thank you.